Welcome to the Problems Channel Season 3, Episode 13, the episode which I titled Binomial Differentials. Slay infinite sums before breakfast, because in this episode we will do precisely that. We will evaluate a certain infinite sum using the little bit of theory that we have developed in the previous episode, in which we discovered a way to integrate the so-called binomial differentials. But before we do that, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the home page of this channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. Find an episode that is of interest to you, use the comment section under that episode, and I will do my best in order to find the time to answer all your questions. In the mathematical problem S3E13, we're asked to evaluate the following infinite sum, in which the summand has the following structure. That is, the summand in this problem is a fraction with 1 with positive unity in the numerator, and the denominator of that fraction looks like a leftover from a certain factorial, that is the number n, which is in this case a positive whole number, n multiplied by n plus 1 multiplied by n plus 2, and so on, multiplied by n plus p, where p is again a whole positive number that is greater than or equal to 2. You can attack this problem in any which way you think you can do it, but in this episode I will share with you my solution of this problem that is based on a little bit of theory that we developed in the previous episode, where we have discovered a way to integrate the so-called binomial differentials. In mathematics, there exists a very significant body of problems trying to solve which we have an opportunity to showcase our creativity, ingenuity, and improvisational skills. However, the trouble is that most of the time in a purely academic setting, it takes many years of a dedicated and a highly specialized training in order to even comprehend the statement of a given problem, let alone generate a solution for one. As such, especially during the formative years, it makes sense to take on problems that do not require many years of highly dedicated and highly specialized training. Yet, on the other hand, with these problems, it is possible to demonstrate and showcase your ingenuity, creativity, and improvisational skills. And putting the problems to prove aside, problems to compute are also very rich with such problems where you can showcase your ingenuity. And these problems usually amount to, for example, evaluating indefinite, definite, proper, and improper integrals, or evaluating sums such as, for example, the one that is shown on the board behind me. Why is that? Well, because when we look at such a sum at the current day and age, we do not really have an industrial strength algorithm that will take a given series on an input and mechanically produce an output for the, let's say, real number that sits on the other side of such a sum. That means that there is no algorithmic guidance when we take on this type of problems. There is no formula into we can plug and chug. And that is precisely the situation where we have to use our own wits in order to generate a convincing story that unwinds, for example, a given infinite sum into a real number that sits on the other side of that sum. And how do we do that? Well, one way to do that is to somehow traverse our web of mathematical knowledge, and from that web of mathematical knowledge try to pluck some fuzzy, let's say, nodes of mathematical knowledge available to us, and then put these nodes together into a coherent and a convincing argument. So here is the problem that was given, for example, on Quora some years ago, and when that problem showed up in my feed, I looked at the solutions that were present at a moment, and I decided to go in this particular way to generate a different solution that was distinct from all the other solutions present at the moment. And this is precisely the moment we try to generate a solution for such, let's say, an open-ended problem for which there is pretty much no algorithmic guidance. This is when we do mathematics. We generate and regenerate, we combine and recombine ideas, because an idea is the first class citizen in mathematics, and all this symbolic shuffling that ensues after that is either lesser mathematics or is not mathematics. Maybe we can qualify it as a mathematically flavored activity, but I want to make sure that everyone in the audience understands that the preparatory work, the quiet time when our mind is at work and our mind again generates and regenerates, combines and recombines ideas, is the time when we do mathematics. When we chase down these ideas, when we try to validate them or invalidate them, this time is again lesser mathematics, let's say. So here, in order to come up with the solution that I'm about to present, you have to spend time, and this is precisely the moment when you have an opportunity to showcase your creativity, ingenuity, and improvisational skills. Now, going back to the previous episode, season 3, episode 12, if you have not watched that episode, you may want to catch up. In that episode, we developed a little bit of a theory according to which we can try to integrate the so-called binomial differentials. And here I have written down the 4 bottom lines, or takes away from the previous episode, where we have 4 formulas for a certain integral. And let's say if, where should I write it? I should write it over here in small font. So we have JPQ. We defined as an integral of 1a plus b times z raised to the power of p times z raised to the power of q, integration carried out over the variable z. So a plus b times z raised to the power p times z raised to the power q. P and q are generally taken to be rational numbers. A and b are taken to be constant real numbers, and that integral comes in 2 flavors. We can leave it as indefinite integral, or we can throw boundaries on it, for example, from a to b, whatever it may be helpful, or let's say c to d, to make it different from the symbols that we have here, c to d. So one way to evaluate such integrals, whether definite or indefinite, is to use the 4 recurrence relations shown over here. And for example, the top 2 recurrence relations that relate an integral j of p and q numbers, p, q, via a similar integral when p is iterated up, for example, and here q is iterated up by 1. These 2 recurrence relations can be used when the numbers p or q are less than 0. Let's say they are negative by iterating them upwards to the vicinity of 0 or something close to -1 or +1 into the so-called terminal case. We may have an opportunity to deal with that case. All the material shown over here requires no computation, but if we can deal with the terminal case, then we can evaluate the integral at hand again when p and q are negative. When p and q are positive, we do the same thing with this integral, but this time we iterate these parameters p or q down by, for example, replacing p with p minus 1 and q with q minus 1. Here we have the top two relations hold. The first one when p is distinct from -1, the second one when q is distinct from -1, and the bottom two relations hold true when the sum of the parameters p and q is distinct from -1. So now here we look at our sum shown over here, where the index, the summation index n, varies from 1 to positive infinity, and the summand has the structure shown over here. We think, okay, so what can we do over here? How can we find a synonym, or let's say a real number, that sits on the other side of that sum? It is equal to something, presumably. How can we attack this problem, and how do we generate a line of reasoning that is convincing on the one hand and correct on the other? Well, first of all, does this sum even converge? Evidently, it does. Why? Because for all the numbers shown in the denominator, with p being greater than or equal to 2, for example, we can write what? In the simplest case, when p is equal to 2, we will write n times n plus 1 will be definitely larger than n squared, because here we will have n squared plus n. N is strictly positive, so we have our strict inequality. It means that the inverses of this will have to have the sign flipped like this, 1 over n squared, and now we have the so-called p series. The p series converges for all p greater than 1, strictly greater than 1, and in this case that means that if our parameter over here p is greater than or equal to 2, our infinite series does converge by the comparison test, so there is hope. The thing is that the way things work in, let's say, real analysis, we have an impressive battery for testing when a given series converges, but there is no, like I said before, there is no any industrial strength algorithmic guidance to finding out what real number, let's say, this particular series converges to. So what do we do over here? From the 4 recurrence relations, which one do we pick and why? Think about it on your own, put this video on pause, walk away, then come back, generate some ideas and compare them to ours. And again, if you find a way to evaluate this sum in any other way, we always want to hear from you. Share your ideas with us in the comment section. But my idea here is the following. We will need the bottom two. We will need the bottom two relations. These two recurrence relations. These two recurrence relations. And why is that? The answer to that question is the following. The structure of the numerator in these recurrence relations. You see, p is by itself, q is by itself, quite convenient. And the idea here is the following. Let's say first we will use the, let's say if we number these recurrence relations 1, 2, 3, and 4. First, we will use the recurrence number 3 shown over here to do what? To iterate or to whittle down p all the way to 0. So in the terminal case, when p is equal to 1, this integral will be what? J of 0 and q. And we will accumulate some amount of material as the multiplicative material in front of it. Then we will take the integral j of 0q, and then we will do the same thing to it, but we will use the recurrence relation number 4 to iterate down or to whittle down the parameter q, again, all the way when q will be equal to 1 in the terminal case. Here there will be the integral j of what? 0, 0 in a certain way, and that will hopefully give us a tactical advantage. And now let us see how that can work in practice. As such, from the menu of 4 recurrence relations that we just saw, we picked the bottom 2. And the idea here is to separately, one by one, whittle down the parameter p to 0, then q to 0, and see what happens. First, which integral? Remember that our integral j pq was defined as the integral of a plus b times z raised to the power of p times z raised to the power of q dz. This is the most general case. We can make this, keep this integral indefinite. We can make it definite depending on what we need. And the numbers p and q, remember, are in general taken to be rational. But here, for this particular deduction, for this particular series, and for this problem, we want to demote these numbers pq, we want to demote them into, evidently, integers. We want to demote them into integers, and given the structure of the summand, because the sum runs over positive whole numbers, evidently we want them to be whole positive numbers. So the constraint p plus q is distinct from -1 will always hold. The number p and q will play out in such a way that they will be positive for us in a few moments, and the constraint will be honored. Here, however, we want to make our integral definite. So what do we pick for the working material, the fodder? Well, let's do this. We will take our integral to be jpq, to be the integral from 0 to 1, 1 minus z raised to the power p times z raised to the power q dz. So what do we have here? Again, where did this integral come from? Well, again, there is no formula. This is the result of us doing mathematics in our mind. We kick ideas around, generate, regenerate, combine, recombine, and that is how what if scenario comes around, and we chase this idea down. Again, don't forget that this actually could be typical, back in my time, a verbal real analysis examination question where in real time, face to face, you spar with the math professor and you tell the story and generate it on the fly, so to speak. So here we think that this particular shape of our integral shown over here may be helpful. And what does that mean? That means that we incarnate this integral as definite with the boundaries of integration: 0 for the lower boundary, 1 for the upper boundary, and we set a is equal to, evidently, 1, b is equal to -1. So far, so good. So now we take our formula. Remember, this is the formula number 3. And how do we cash it in for these particular values of the real numbers a and b? Well, in this case, our integral j pq as a recurrence relation where we will whittle the parameter p down by 1 will be what? 1 minus z. So we write down 1 minus z raised to the power of p times z raised to the power of q plus 1 over, what do we have here? We will have p plus q plus 1. But this time, because our integral is definite, we take this free-floating term between the boundaries of 0 for the lower boundary, 1 for the upper boundary, followed by these terms. So what will we have here? There is no b, a is plus 1, so plus p over p plus q plus 1 times the integral of j p minus 1 q. You see, this is how we did it. This is mostly mechanical work. There is not much intellectual voltage. We simply exhibited, or we expanded our voltage. We did mathematics when we came up with these original ideas. Now we just run this idea down and see what will happen if. Now notice that at the upper boundary of integration 1, this free-floating term will vanish due to the factor 1 minus z raised to the power of p, because when z is equal to 1, 1 minus 1 is 0. It annihilates this free-floating term once, and the second time when z is equal to 0, this free-floating term will be annihilated, and it will vanish due to this factor right here, z raised to the power of q plus 1, 0 times 1 raised to the power of p over a constant real number is 0. So the free-floating term always vanishes in our case. This was in some sense as you can see now, the motivation for the structure of the integrand in this case. So now let's write down in a more succinct fashion our integral with these particular values will be what? P over p plus q plus 1 times the integral of p minus 1 q. Now the question is, when we begin iterating p down by stepping it down by one, what will the shape of this multiplicative constant in front of j be? Well, let's see. The second time we iterate, let's say we will write it down like this. It will be p times p minus 1 divided by, here we will have p plus q plus 1 times p minus 1 plus q plus 1. That much is understood. This term comes from the, let's say, first iteration. This piece comes in as the second iteration. And what will be here? Here we will have j p minus 2 q. You see, this is very straightforward maneuver. So what we do now, what is the objective of this exercise? The objective of this exercise is to iterate p down by 1 into what? Until we have this argument of our integral becoming 0. Well, will it happen? Well, it will happen precisely when p is equal to 1. And once we continue this process, and we repeat these iterations by replacing p with p minus 1, for the third time, what factor will be here? P minus 2. Over here we will have p minus 2. Over here we will have what? P minus 3. So by the time we whittle p down all the way to 1, we will have exactly p very nicely shaped factors that will amount to what? P factorial. It will be p factorial. What will we have in the denominator in this case? Well, look at this. We run p down all the way. So how can we capture this symbolically? Well, this will be the product k plus q plus 1, where k varies from p to 1. You see, where k varies from p to 1, we step it down. What will be the integral over here? It will be 0 and then q. You see? So this is our integral. Let's put it down, write it down officially. This is the result that we were trying to produce. That's what we were gunning for. When we did what? When we used our formula shown on top, the formula number 3, out of the general form of the essentially binomial differential, we picked This one, we showed that the free floating term over here over the given boundaries, 0 for the lower, 1 for the upper boundary of integration, vanishes at both boundaries at all times. So this free floating term is not something that we have to worry about at all. This is the only piece that is left over. We wrote it down over here, and now we simply iterated p down, p times p, p minus 1, p minus 2, and so on until p became 1. And this argument in the designation of the integral became what? It became 0. So now, once that is understood, we will essentially do exactly the same thing, but this time we will whittle down, or we will iterate down the parameter q. Very well, we now do to the integral j0q the same thing that we did to the integral jpq, but this time we whittle down the parameter q down by 1 using the formula or the recurrence relation number 4. I wrote down this recurrence relation on top over here. Make sure that you catch the difference. Here, the linear combination is raised to the power p plus 1, and the sole factor z raised to the power of q, not q plus 1 q. Here we have b in the denominator of the fraction. Here we have the minus sign, a times q, not a times p, but a times q, q. And we have again b in the denominator. We have our constraint. We still use the same choices for the numbers a, which is positive unity, and b, which is negative unity. And then we take our integral j0q, and this time we incarnate this formula not only with the numbers a is equal to 1 and b is equal to negative 1, but we do also what? We set p, the parameter p, to 0, because remember in the previous segment we whittled it down all the way to 0. So here, when p is 0, what do we have? We have b for negative 1. There is a minus sign over here. 1 minus z raised to the power p, but p is 0. So p plus 1 becomes what? 1, power number 1, so the first power. Z is raised to the power of q. P is gone, q plus 1 is left, q plus 1 is left, over the boundaries of which ones? 0 for the lower boundary, 1 for the upper boundary. Negative b becomes minus times minus 1 plus, so this is the plus. A is the positive unity, so q over q plus 1. Again, why there is no p? Because in this case p is 0. Remember, we whittled it down. Now, times what? J, the integral j of p, but this is 0, and then q minus 1. This is what we use. This is the little engine that will iterate q down, and through each iteration we'll slug in new multiplicative constant in front of the corresponding integral. Now, what happens with the free floater term as well? Well, at the upper boundary of integration, which is z is equal to 1, this free floating term vanishes due to this factor 1 minus z. 1 minus 1 is 0. 0 times 1 or any other real finite real number constant is 0. And at the lower boundary of integration, when z is equal to 0, this free floating term is taken out by this factor over here, 0 raised to the power q. 1 minus 0, 1. 1 over q plus 1 is a constant real number. 0 times any such number is 0. 0 minus 0 is 0. So this free floating term again vanishes at both boundaries of integration. So now we have only this summand left. So let's write down this result in a nice way over here separately so we understand what is going on. Q over q plus 1 times j0 q minus 1. And what do we do over here now? Well, we do the same thing. We run down q by 1 unit, by negative 1, by replacing it as follows. Q in the in each iteration is replaced with q minus 1. So what will we have over here? Let's write down a couple iterations. Q over q plus 1 times q minus 1 over q minus 1 plus 1 times j of 0 q minus 2. You see, this iteration is very straightforward. We take this formula, we use it over here, but here on the right hand side of this formula we replace q with q minus 1 uniformly or mechanically anywhere we see the symbol q. So we keep the previous factor of q over q plus 1, q over q plus 1, but we multiply it by what? Q becomes q minus 1 in the numerator, q becomes q minus 1 in the denominator, and we iterate q down by 1 in the second argument of our integral. That's it. Game over. We keep rolling like this, and after we bring again, because our little engine that could has q minus 1 as the second argument of our integral j, when will this argument become 0? This argument will become 0 when q will become 1. So how many such factors will we have? Well, we will have the following formation over here. We will have q times q minus 1 times q minus 2, and so on. The last factor will be 1. And here in the denominator we will have what? Q plus 1 times 1 less q, q minus 1 plus 1, times q minus 2 plus 1, and so on, until we have what? Until we have some number that looks like 1 plus 1 times j 0, 0. And what do these formations tell us? Well, these formations tell us that here in the numerator we have the nice factorial of q, Remember, we demoted our parameters p and z to be, in this case, positive whole numbers, so the factorial of a positive number does not require the introduction of any new ideas. In the denominator we'll have the product that runs which way? It will be, let's say, j plus 1, where j varies from q to 1, and here we will have the integral j 0, 0. This is our terminal case. So here let's connect the dots. This is our integral j 0q initially. This is the result that we were shooting for. Again, there is nothing very complicated over here, very little if anything. I would even say zero intellectual voltage, because simply we generated the voltage, so to speak, when we came up with an idea to do this. But then once we run this idea down, it's mostly mechanical, and we just see what will happen. Now that we have the result from this segment, and now we're going to take the result from the previous segment and glom them together, and we will find an interesting representation of the integral shown over here. Let us now combine the two results that we obtained in the previous two segments. That is, we take our integral j of p and q and glom the two products together. Our first product was p factorial over the product that runs as follows: k plus 1 plus q, where k varies from p all the way down to 1, p minus 1, p minus 2, and so on. The second part of that product was q factorial over the product that runs as follows: j plus 1, where j varies from actually q to 1 when we whittled q down as follows: q, q minus 1, q minus 2, and so on, times, in the first case, it was the integral j of 0 and q minus 1, or in this case, once we whittle both of the numbers, whole numbers p and q, down to 0, it is integral j of 0 and 0. Now the question is, what is the terminal case of the integral j, 0, and 0? Well, it is less than trivial. We take our representation of the integral here, jpq, substitute p equals 0, q equals 0, 1, 1, 1 times 1 is 1, carry out. So this is the triviality itself. The integral j of 0 and 0 is the integral from 0 to 1 of the variable dz. This is the variable z itself. Integrated between the boundaries of 0 and 1 becomes what? 1 minus 0, which is 1. Wonderful. We now write down our result. P factorial times q factorial times 1. And now we just have to deal with this animal. This animal may look scary at first blush, but it is not really. If you cannot see right away that this product is actually the factorial of the number called p plus q plus 1. And in some sense, when you try to deal with these expressions, you see that the plus 1 is present in both of these factors. So in some sense, mentally, in your mind's eye, you can drop it. You do not really need it because it's present in both. And then once you're done with your manipulations, you simply plug it back in. So here is one way to deal with this type of products, is to cache them in, or in some sense reincarnate with specific numbers. So let us say the number p is equal to 3 and the number q is equal to 5. Write down the string of products that is shown over here in the general form with these specific numbers. What will we have? On the left hand side over here, simply playing out this product left to right by following the recipe. 3 plus 5 plus 1 times p, which is 3, becomes 1 less. 2 plus 5 plus 1 times 1 plus 5 plus 1. And then once p reaches 1, we are done with unfolding this product, and all the while we multiply this product by another product, which is what? 5 plus 1, 4 plus 1, 3 plus 1, 2 plus 1, 1 plus 1, and this is it. So what is this number? Well, look at this. Read this string in reverse order, so to speak. Instead of left to right, scan it right to left. What will you see? Well, you see one number increased by 1, increased by 1, by 1, by 1. Here we have 5 plus 1, another 1, another 2, and so on. What is this? Well, there is no choice. It is 3 plus 5 plus 1 factorial. Game over. So now we have our representation that we were trying to generate, and this is the result that we take on, and we massage this result further as follows. If you were solving this problem this way, what would be your next maneuver be? Well, here is a winning maneuver. Replace uniformly, which means mechanically, the symbol q, the symbol n minus 1, as shown over here in red. Q becomes n minus 1. So in this result, which we obtained as was explained in the previous segment, we roll through this result, and uniformly, meaning mechanically, every time we see the symbol q in that relation, we replace it with the symbol n minus 1. Q becomes n minus 1, q becomes n minus 1, q becomes n minus 1. So thus, under this substitution, when q is replaced with n minus 1, we have the following result. The integral from 0 to 1 of the following integrand, 1 minus z raised to the power of p times z raised to the power n minus 1, this is important, n minus 1 dz, is equal to p factorial times n minus 1 factorial divided by, what do we have in the denominator? p plus n factorial. Now, do you see anything familiar or anything that is advantageous to us? You should, because this is where, in some sense, this is where the gold is if we rewrite our result shown over here a little bit as follows. Wonderful, we can now bring home our result and rewrite the formula that we obtained in the previous segment as follows. Move the p factorial from the numerator of, let's say, right hand side to the denominator of the left hand side. And here we have the following product: 1 over p factorial times the integral from 0 to 1 of the following integrand: 1 minus z raised to the power of p times z raised to the power of n minus 1 dz is equal to n minus 1 factorial over p plus n factorial. And what would you do here if you were solving this problem this way? What would be your next maneuver be? Well, the next maneuver here is to unfold this ratio of factorials, and here we observe what? Well, in the numerator, what do we have? What numbers do we have? We have 1 times 2 times 3 times 4 times n minus 1. Let's say n is 5, 4. And what do we have in the denominator? Well, here we will have exactly the same string of numbers: 1 times 2 times 3 times 4. When n is, let's say, 5, so we stopped at n minus 1. Then we will have 5. We will have n times n plus 1, n plus 2, n plus 3, until we reach the number p. So the first two products in the numerator and in the denominator cancel out, and what will we have left as a result? Well, we'll have 1 left in the numerator, and in the denominator we'll have precisely the numbers that we are given in our infinite sum: n plus p. You see? This is exactly what we have. This is a trivial exercise. In some sense, this is nothing beyond middle school arithmetic again. It's not complicated. So what do we do now? Well, now you should see that what we do is, let's say we rewrite this relation, we omit this result, we drop it, we connect, glue these two results together, the right hand side, the left hand side, and then we switch them around just to make it more traditional, if you will. So here we will have this number over here, n times n plus 1 times n plus 2, and so on, n plus p. This is our sum. Here we have 1 over p factorial, integral from 0 to 1, 1 minus z raised to the power of p times z raised to the power of n minus 1 dz. What is the next maneuver right now? Correct, we sum both sides over n from 1 to positive infinity on the left hand side. We do the same on the right hand side. This is a plus infinity. So what do we have here? Well, this is our sum sigma. This is what we are required to evaluate. And what have we managed to do? Well, we have managed to express our sum as a certain integral. You see, in general, this is actually a very deep, very, very meaningful, very interesting phenomenon in mathematics, when one thing is equal to another thing. Like I said, it's a very deep and meaningful phenomenon in mathematics, deserves its own entire book, maybe several books. But for us, tactically, what is important here is the following. Sometimes, what do we have here on the right hand side of this result? On the right hand side of this result, we have two limits, and it all comes down to the question of, can the order of the limits be switched? Technically, that means, can we move the summation sign through the integral sign under the integral sign? We need to prove that this is possible. It is not possible always. Sometimes it is possible, and in this case, it is possible. We can move the summation sign through the integral sign, and what we can do here is rewrite our integral representation of the given sum as follows. As the sum, we will bind this sum not to this factor because there is nothing, no material depends on n, so we bind it to the material, all the material that depends on n, from 1 to positive infinity, but this is z raised to the power of n minus 1 dz. You see, again, we have to be careful when you do this work for publication, for peer review or whatever. You need to prove that it is legal to move the summation sign through the integral sign, or the other way, if you can move the integral sign through the summation sign out and technically swap the order in which the limits are taken. It is not possible always. Sometimes it is possible. In this case, it is possible. So now what do we recognize here? Well, this is the good old infinite geometric series, and we know how to sum those. Let's see, we write down the result. Which way? We know that, let's say, I will write it over here for you guys this way. Let's say this way. This is none other than 1 minus z. For example, if we replace n minus 1 with, let's say, uppercase n, this guy, lowercase n with the uppercase n plus 1, when lowercase is 1, n is 0, so technically we have a sum that runs from 0 to positive infinity, but this common term is raised to the power n. And the sum of infinite geometric series is known to us. This is our favorite expression, 1 minus z. So what do we have now? Now we have the following result. We have the following result. 1 over p factorial times the integral from 0 to 1, 1 minus z raised to the power p minus 1 dz. You see, we have 1 minus z raised to the power of p in the numerator, 1 minus z in the denominator. So we simply change the power of p from p to p minus 1. And how can we rewrite this integral? Well, let's do it this way. We will, now that we understand this string of manipulations, very nice. So what we do here is the following. We move under the differential the material that we have here. So we write 1 minus z. See, and we put the minus sign over here. So that maneuver is understood. So now we have technically the integral of t raised to some power dt. This is a trivial integral. We do not have to worry about it too much. Let's write it down over here. It will be minus 1 over p factorial of 1 minus z raised to the power of p divided by p over the boundaries from 0 to 1. So what do we do here? We bump the power by 1 and we divide the result by that increased number. So what do we have here? We have minus 1 over p factorial. When z is equal to 1, then 1 minus z becomes 0, 0 raised to the power of p. P is a finite, let's say, real number, 0, so the whole thing vanishes, and then we have minus. So we'll have 0 minus, when z is equal to 0, this term becomes 1, 1 raised to the power of p, 1. We have 1 over p, so minus 1 over p. And what is the bottom line here? Minus times minus is plus. So voila, we have our answer. P times p factorial. And we now can write down this result. Let's write it over here as an official result. Our sum that we were asked to evaluate from 1 to positive infinity of 1 over n times n plus 1 times n plus 2 and so on times n plus p is equal to 1 over p times p factorial, provided that p is greater than or equal to 2. This is the result. And for those of our viewers who studied during our first and second season the so-called problem-solving approaches in a dedicated manner, how would you qualify this solution that we came up with in this episode? Well, first, remember, what we did is technically what we achieved over here when, in a very deep and meaningful, mathematically hefty way, one thing is equal to another. Technically, we did a transformation. We transformed our naked, so to speak, sum into an integral representation. That is number one. And then we managed to reduce our result to an integration that can be carried out in the so-called closed form or as a finite combination of elementary function. So in some sense, it's transform and reduce. So this is all courtesy, as I promised in the title of this episode, courtesy of the little bit of the theoretical machinery of integration of the so-called binomial coefficients. And once you understand how this result was produced and how we came up with this notation over here with this result, you can actually craft different numbers over here by playing with this n and p, by playing with the quality of n. For example, even numbers, odd numbers, or some funky combination with the p, it becomes possible to evaluate this type of sums by reducing them, by basically reducing, you see, transform and reduce, in reducing them to basically an integral. And sometimes these integrals are quite pleasant. They're all computable in closed form or representable as a finite combination of elementary functions, all courtesy of binomial differentials, which slay infinite sums for before breakfast. Now, this is it for the problem S3M8, and we will move on to a new challenge next. Our next challenge will be a problem in physics, numbered S3P3. Remember, with the letter P, we designate problems in physics. So the next challenge will be the problem in physics, S3P3. And in order to keep the mood light in a funny and humorous way, here we're given two proverbial spherical chickens of uniform density. One of these chickens will be hollow, the other one will be solid. So technically, we're given a material sphere and we're given a material ball. The radii of a sphere and of a ball r sub s and r sub b are one and the same. So the radii of these two objects of revolution, let's say, are equal one another. So equal radii. And the mass is also equal. The mass of a sphere and the mass of a ball is one and the same. So m sub s and m sub b, s for sphere, b for ball, is also one and the same. Without, let's say, no tapping, without knocking on these objects, no tapping and no knocking on these objects, using the methods, let's say, of classical mechanics, we're asked to discriminate one against the other. In other words, we need to come up with a way to produce with absolute certainty, correct answer, which object is which. At the end of some machinations that we uh, put these objects through, presumably we will say with absolute certainty this is a sphere and this is a sphere, and with absolute certainty this object is a ball and it is a ball. And this is it pretty much for the formulation of the problem statement. So basically, of equal radii, we're given two objects, a sphere and a ball. The masses of these two objects are the same, using the methods of classical mechanics without tapping and without knocking on these objects. We are asked to distinguish or discriminate between the two with absolute certainty and correctly. And the next few seconds, for those who are still confused by what is going on, remember, on this channel, under the courses tab, you can find I have several courses. One of these courses is called Inversive Geometry. In the first or second introduction to this inversive geometry course, I explained the difference between a circle and a disk. In your opinion, what do you think? A circle is a one-dimensional or a two-dimensional object? The correct answer here is that a circle is a one-dimensional object because one real number is required to describe completely any point that belongs to a circle, because a circle, let's say in a properly chosen Cartesian coordinate system, has the following equation: origin centered and all this beautiful stuff, x squared plus y squared equals to r squared. And the reason why a circle is a one-dimensional object is because one real number, and that number can be called theta, the angular displacement, theta, is needed in order to completely describe any position, any point that belongs to that object, that is a circle. Now, a disk, on the other hand, is a two-dimensional object because a disk, origin centered in the properly chosen Cartesian coordinate system, will have the equation of what, x squared plus y squared less than or equal to r squared. And then in a disk, we will need two real numbers: the radial displacement of a point. So we will need rho, which varies between 0, let's say, and r, the radius of the disk. And then we will need the angular displacement, theta, two numbers, theta and rho. We do not need this number rho in case of a circle. Likewise, a sphere is a two-dimensional object because two real numbers, two angular displacements are needed in order to position any point, to completely describe the position of any point on that object, completely describe this. The ball, on the other hand, is a three-dimensional object because three real numbers are needed in order to completely describe the position of any point that belongs to this object. What are these two numbers? Two angular displacements and one radial displacement. How far is this point within the ball displaced from the center of that object? So here, when we say a hollow sphere, what a mathematician really hears is wet water. We do not really need to say that a sphere is hollow and the ball is solid. It is understood by the names. What is understood by the names of this object. A sphere is an object that is hollow, and a ball is an object that is solid. So in this problem, with no tapping or knocking on the ball, using the methods of the apparatus of classical mechanics, we are asked to discriminate one object from the other with absolute certainty and correctly. If the radii of these two objects is one and the same, the radii are equal, and the masses of these objects are equal as well. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the problem S3P3. And in this solution, I will present 5 distinct enough ways to distinguish a sphere from a ball.